Hello, everyone, and welcome to today's public webinar with TPC entitled Fuses and Circuit Breakers, What You Need to Know. My name is Ryan Smith, and I am joined here by our presenter and host, Bob Kluke. He's been in the industry and the electrical industry as a master electrician, as well as many other trades and jobs throughout the years, decades, in fact, of electrical work around this country. So lots of experience he brings to the table, and he's one of our expert instructors at TPC in the classroom as well. So we're going to learn directly from the source here about fuses and circuit breakers, their importance and their function within our electrical circuits. Before we jump into the webinar today, I want to just give everyone who's here today a little bit of an intro to what we have here today at the webinar. First and foremost, this webinar is being recorded, and this video recording of this presentation will be made available on our website within about 2 business days. So be on the lookout for that. The second thing we want to let you all know is that the PDF of these slides will also be made available and downloadable from our website. So that means you don't have to worry about, screenshotting what you're seeing or anything, or trying to jot down quickly what you're seeing. You should be able to see this all back later on. And then finally, this session is live today as we're presenting. And for that reason, we want this to be as interactive as possible with you who are listening in. And so when you see the bottom of your screen, you're going to see a Q&A button, the questions and answers button. We'd love for you to click that Q&A button and type in any questions or curiosities you have for Bob throughout today's presentation, and we'll be able to answer those questions before the end of this hour-long session together. And then finally, since this is a public session, we're not offering a official completion certificate or certification for this bit of informational learning. However, we do highly encourage you take one of our official 2-day courses to get one of those completion certificates for maybe your continuing education for your license or for other means of learning. Before we officially jump it over to Bob, I would love to get started with one interaction piece, and that is a little poll to learn a little bit more about who's here today. And you're going to see just a couple questions showing up on your screen on a window that pops up right now. And you can answer these 2 questions to the best of your ability. First one is, when performing maintenance on circuit breakers, which of the following do you utilize at your facility? Do you use NFPA 70B, infrared thermography, ultrasound testing, all the above maybe? Or you can select any that apply. And then secondly, when a circuit breaker trips, what do you normally do? Do you reset the circuit breaker? Do you troubleshoot the circuit breaker? Do you try to locate the reason why that circuit breaker tripped? Or do you call an outside contractor to get help? Try to pick the one that fits best for your scenario. Okay, we got a lot of you coming in with your answers. I'll give you just a few more moments to provide those answers for us. Okay, good. We're getting a good spread of answers here. All right, the answers are about evening out here. So I'm going to go ahead and end the poll and then share the results with you. So the most of you did respond with NFPA 70B. 50% of you responding said you are using the information in NFPA 70B. We're going to, for the 50% of you who did not answer this, we're going to kind of go into that today and what the importance is of NFPA 70B. 40% of you are using infrared, which is great to see, and we're going to talk a little bit more about that today. And then for the second question, we're glad to see that 56% of you, the biggest majority response was the first thing you do when your circuit breaker trips is you locate the reason why it tripped. I know it's a very, very tempting to, I know personally I've felt this temptation many times to just reset the circuit breaker and get back to the process running. We're going to talk about the reasons why we might want to avoid doing that in today's session. So I'm going to go ahead and stop sharing. So you should have seen that window disappear from you, and what you should be seeing full screen now on your side is the title of today's session, Fuses and Circuit Breakers, and Bob's presentation. So without further ado, I'm going to hand it over to Bob. Thank you so much for being here, Bob.
Thank you, Ryan. Thank you for the introductions. Thank you for all the attendees that have showed up this afternoon. Really appreciate it. Topic today, like Brian said, fuses and circuit breakers, overcurrent protection. So what we really need to know. So for some of you that said, 30% of you said that you reset that breaker when it trips off. want to give you an idea about that in OSHA 1910, which is federal law, they really want us to locate the reason why, because if that circuit breaker tripped off because of an short circuit or ground fault situation, just by resetting it could cause uh, some unwanted incidents. So, and we'll talk about those a little bit. And so that one I wanted to address right off the bat. Okay, so first of all, circuit breakers and fuses I could throw into this discussion uh, protect equipment. They do not protect people. So, as far as us go, or people, right, we can get locked onto a circuit at 40 milliamps. Well, even the lowest fuse that I'm probably going to put in a circuit is a 1 amp circuit. So that's not going to protect me. I'm nowhere near 1 amp yet. So we are really looking at equipment here that is designed to protect our facilities and whatever we have inside those facilities. Of course, a circuit breaker is very handy because it is an automatic device. I can reset it. I don't have to replace it like I do a fuse. And so notice this also, that what causes it to trip, either an overload or a short circuit or ground fault. And so overload is just a little bit over the rating of the equipment, right? So if I've got a motor that draws 27 amps, well, 35 amps would be an overload, right? But a short circuit or ground fault situation, that is all the current that the transformer or power source can deliver. And so sometimes that can be very high. I'm just going to give you a few examples that the short circuit current at my house, which is very typical at my house, is right around 2,500 amps. Now, I'm doing this broadcast from a hotel. The short circuit current at this hotel, 23,000 amps. So it all depends on the size of the transformer that is feeding our facilities. And so this is going to be very important for us to remember, that a short circuit or a ground fault is all the current that could flow. And we're going to have a rating on that for our circuit breakers and fuses, and we will see that coming up. Of course, how do they work? They are going to open the circuit. When we have an open circuit, no current can flow. Circuit opens up. We want to find out why. Go make that repair, and then reset the breaker. And so the circuit breaker does this with some mechanical parts, and we're going to take a look at some of these mechanical parts coming up shortly. So here's some of the items inside of it. It does have an electromagnet that is going to be in there to help us with our fault current or short circuit current. It is going to have a bimetallic strip, which is going to help us with overloads. It's going to have a moving contact, because at times my circuit breaker is going to be open. At other times, my circuit breaker is going to be closed. So we've got to be able to move some contacts to close those and open those. It can act as a switch if it is marked SWD or HID. So the circuit breakers have many markings on them. Uh, an SWD, switching device, HID, high intensity discharge lighting, both allow the circuit breaker to operate as a switch. It will have our stationary contact. It'll have some terminals that we're going to connect our um, line side and load side to. And it's got to have a mechanical catch to keep it in place when we have gone ahead and turn that circuit breaker on. So here's a little bit better, a little pictorial of it, right? Over here, and these are molded case circuit breakers, and we're going to be looking at different types of circuit breakers today, some that are not molded case, but these are just our regular thermomagnetic circuit breaker that we would go buy right off the shelf, that probably in our homes or in most of our facilities, right? And so this part, the bimetallic part, is for overloads. And so when too much current is flowing from our line side here up through this magnetic element over here to my bimetallic strip, when too much current flows there, it tends to bend that piece of metal. And when that piece of metal bends, it is going to hit what we call a trip bar. And then the circuit breaker would actually trip, the latch would open up, and these contacts right here would open up on an overload. Now, I have seen some circuit breakers on overloads that the bimetallic strip might not be working as good as we would like it. And so I have seen equipment melt because the bimetallic strip just did not do its mechanical job and get over there and open up that latch. But normally speaking, they do a great job. It could be that maybe we didn't maintain the circuit breaker properly or whatever, but on overloads, we are dependent on two pieces of metal, and when that current flows through there, that current is going to make one of those pieces bend and open the breaker up. Now, on short circuits or ground faults, when we have all the current flowing, right, we are going to use a magnetic coil. It is going to sense that we have all this current flowing, and it's going to act much quicker. And so that's going to operate on a molded case circuit breaker around 2/100ths of a second. So pretty much we got about a cycle and a half of electricity. But remember, this could be very high. At the hotel here, 23,000 amps could flow for a cycle and a half. And so we have to have a circuit breaker that can withstand that amount of current. And in a minute, I'm going to tell you where that rating could be found. But here we can see all the different parts. So our contact that we can manually close these contacts by just reworking our switch. These contacts automatically are going to open on overloads by the bimetallic strip, or they're going to open with the magnetic coil because of short circuit or ground fault. So that's basically how a circuit breaker works. And but remember, there are some National Electrical Code considerations that we have to look at. That our normal circuit breakers are rated to operate at 80% of the load. So, for instance, if I have a 20 amp circuit breaker, it can continuously carry 16 amps with no issues. We get above 16 amps for a rated amount of time, and it's going to start that process of the bimetallic strip to start to bend. That's fine. Breakers can be rated all the way up to, this says up to 2,500 amps on a molded case breaker. When we get into the different types of breakers, you'll be able to see that we can have breakers all the way up as high as we want, maybe 6,000 amps, but on molded case breakers up to 2,500 amps. And then it comes to interrupting rating. This is extremely important for us to understand. This is true about circuit breakers or fuses. And so on the side of my breaker, if it is a molded case breaker, on the side of it, I am going to have what they call an IR rating. We used to call it AIC. Now it's IR. And it is going to be marked. And for residential applications, that interrupting rating is going to be 10,000 amps. So in a residential situation, my circuit breaker can safely interrupt 10,000 amps, which is pretty good because the short circuit current would never really get above this number in a residential application. Now, when we get to commercial or industrial facilities, we can see that it could be 10,000. These are all KA, so got to multiply each one of these by 1,000. Or look, could be up to 200,000 in some facilities. Depending on the size of the transformer, the larger the transformer will be the larger that my fault current is going to be. So I have to be able to determine what that interrupting rating is. because we have a federal law in OSHA 1910 that says this: my interrupting rating has to be greater than whatever the available fault current is. So I told you at this hotel I'm at today, the fault current was around 23,000 amps. And that's true. That means that my interrupting ratings on my circuit breakers better be higher than that. And so I don't really want to go with 25. That's kind of close. I think I'll go with 30,000 amps. Because here's what happens if that interrupting rating is lower than the available fault current. The circuit breaker or fuse will explode, and it's going to sound like three sticks of dynamite just went off. And so that has happened in many facilities, right? We just did not pay attention to the interrupting ratings. Normally, what we would pay attention to is the rating on the handle. Oh, is it a 20 amp breaker? Is it a 40 amp breaker or whatever it is on the handle? Well, that's fine. And that would protect my conductor, no doubt about it. Um, Other than a motor circuit, it probably protect my equipment. But we have to pay attention to what's on the side of the breaker and not always what's on the handle. And what's on the side of the breaker would be the interrupting rating, and make sure that it is higher than whatever the available fault current is. Now, on some different systems, which they're talking about here, some corner grounded delta systems or some maybe some resistance impedance grounded systems, they could have a lower interrupting rating because we are limiting the amount of ground fault current with these different types of systems. So I want you to really remember about interrupting rating on the side of our breakers. Extremely important. And we can going to be able to see a couple here. So this is a 150 amp breaker on this side, but its interrupting rating is 10,000. Over here, we have a different rating on the breaker. This is a completely, I cut these two breakers in half. One is over here, the other is over here. On this one over here, we can see 22,000 amps. A lot of other information on these breakers, just so we get a good idea, right? So if I increase this just a little bit and zoom in, and so we can see that this breaker on this right-hand side, it is for 240 volts AC. That is it, nothing else. And so this would be used on a system that was 240 volts. I have to use at least 75 degrees Celsius wire. It can be copper or aluminum. There is a torque setting on this breaker that I have to make sure I adhere to. And they tell me the size of my wire can be anywhere from number 4 up to 300 kc mil. But the interrupting rating on this one, 22,000 amps. So very important that we know that interrupting rating so that we can eliminate some of these explosions that we want to stay away from. Now we're going to get into breakers that might be a little bit larger than the molded case breaker. So this one here, thermomagnetic circuit breaker, and also known as inverse time. What does that really mean? When that current skyrockets up because of the fact we have a short circuit or ground fault, then the clearing time is going to be much quicker. And so the magnetic portion of the breaker is going to act much quicker than the thermal portion of the breaker. And so on a short circuit or a ground fault, it could be that we could open up that circuit in a half to one cycle. So right around 0.01 hundredths of a second. And these can be also be adjusted. And so I can adjust the setting on this breaker. That's no problem. Current limiting breakers, these are going to help limit the amount of fault current that can come through the circuit. Really helps us with arc flash issues. So they're going to open the circuit so fast that we're not going to allow the air to ionize and turn into a conductive plasma. What's the difference on these larger breakers that are current limiting? They've got blow apart contacts. And so they've got also arc extinguishers, we'll put another coil in there to help suck the arc away from the contacts. And so these breakers also are going to limit much damage to any component downstream. Why? Because of their fast clearing time. And so they're gonna help us extremely well with that. And so here we can see an insulated case circuit breaker. They are larger in physical size, right? They can be all the way up to 5,000 amps. We can see their interrupting ratings. We could also make adjustments on this one for short time delay option if we had motors connected to this, or instantaneous trip. Also, a ground fault setting. And so we can set all these settings with these larger case breakers. Uh, Low voltage power circuit breakers. Um, these are used in industry all the time, especially when selective coordination is either mandated or desired. So let's take a little bit of look at selective coordination for a bit. So let's say somewhere in my facility, I have a motor. Feeding that motor, I've got a fused disconnect. So there's one overcurrent device right here. This fused disconnect gets its power from the closest panel, which is going to have a circuit breaker in that. And this would get its power from our main distribution panel that's going to have some circuit breakers in that. And then we have our switch gear somewhere. So one, two, three, four overcurrent devices before I get to my motor. What does selective coordination mean? It means that the overcurrent device that is the closest to the equipment, so this fused disconnect, should have the quicker clearing time. And so the quicker clearing time is going to clear just the motor. That's the only place we have the problem is at the motor. Let's get rid of our problem with the first overcurrent device. Can you imagine if we used the switchgear to clear this problem? Because if we did, we just lost power in our whole facility. So really not a good idea. So these do allow us to achieve selective coordination much better. We can maintain these breakers. They're usually in a cabinet that we can rack them out. We can de-energize them by racking them out, getting them away from the cabinet. We can clean the contacts with some electrical solvent. We can ohm out the contacts. We can put it back in and adjust any of our trip settings. These breakers can all be programmed. And so these are just a little bit larger breakers, but they are really good to help us achieve that selective coordination that I was talking about. And I said breakers protect equipment. That is true until we get to some specialized breakers. And so this is a GFCI circuit breaker, and we can see that it does have a um, range that it's going to trip at for ground fault current between 4 to 6 milliamps. That UL standard 943 on circuit breakers was adjusted in 2008, and they do allow this ground fault current now to be only 6 milliamps or more to help us with nuisance tripping a little bit. And so these are Class A devices. That means that they are going to trip at 6 milliamps or more. And these will protect equipment and people, both. So because of the fact that on a ground fault, which means the current is flowing somewhere that we don't want it to flow, which if it is through a person, we're going to save that person by de-energizing that circuit um, in 1/240th of a second before it ever gets a chance to get to 40 milliamps. Another special circuit breaker that we have in today's world is an AFCI circuit breaker. These were introduced into the National Electrical Code in 1999. We had to start installing them in 2002. They were first limited to just residential applications, but now these need to be installed in hotels um, and other areas where we might be in there for an extended period of time. And what these are protecting us against is if there is a loose connection behind the wall, then we can go ahead and de-energize that circuit and protect that building before it burns down. So AFCI breakers are still protecting structures or equipment. The only one that really protects people is the GFCI circuit breaker. So that would be it. Going to talk about fuses some also. So when I first started in the trade, fuses were very prevalent. And one thing about a fuse is this: we can tamper with them. And so when we first started with fuses, here's what we would discover if we put a 15 amp fuse in and we had too many uh, appliances or pieces of equipment on that fuse, the fuse would open up and we would be without power. So they would take the 15 amp out and put a 20 amp fuse in, and that would compromise the integrity of our conductors, and it would could damage equipment also. So now in today's world we have non-tamperable fuses, but I can tell you that if we are trying to protect a piece of equipment and we want it to be responsive to overloads, sometimes fuses are a little bit better than that bimetallic strip that we have in breakers. So on overloads, these are pretty darn nice. And these can be single element or dual element. They're going to have a fusible link that can melt and open the circuit and protect whatever we have. So on a dual element, right? They a lot of times we'll use these on motors or transformers that have coils inside and have a large inrush current. We want to make sure we allow the motor to start. And so we'll allow a higher current to go through for a specified time. And then we're going to go ahead and protect it after we have timed out. And so we're going to allow maybe 10 times the amount of current to go through this on startup of a motor. And then when it comes back, this will definitely help protect against short circuits on a motor, no doubt about it. Of course, on a motor circuit, we have overloads that help us with the overload protection. But dual element time delay used a lot where we have a high amount of inrush current. On these, on the overload operation, there's basically going to be a spring in there, which is going to trigger the connector to open up, and it will just open that circuit up. So that is what's going to happen on that particular fuse. On the short circuit operation, we're actually going to melt something, and it is going to melt very quickly, and we're going to be replacing that fuse. So right here, I do want to say this, that if I did want to check one of these fuses when they were out of the circuit, I could go ahead and put my ohm meter on one side or the other. And if I saw something close to 0 ohms, of course, I would know that fuse was good. If I did that same test and I saw OL on my meter, which is open line, then I would know that circuit, that fuse had opened up that circuit. And towards the end of the presentation, I am going to give you an idea how OSHA does allow us to test these fuses while they are energized. So I'll definitely go through that also. So some fuse ratings, and this would be all in Article 240 of the National Electrical Code. And these fuses, standard fuses, can be anywhere from 1 amp all the way up to 6,000 amps for fuses. And so they can, and then they can have different interrupting ratings, right? They can be down as low as 10,000 or up to 300,000. So remember on the interrupting rating that it is going to be the amount of fault current that it can safely interrupt. Article 240 is also going to tell us that on Edison-based fuses, they have to be non-tamperable. So we're not going to be able to put in a higher ampacity fuse than what is needed for that circuit. But I really want to stress this, that when we replace a fuse, we want to make sure we replace that fuse with the exact same fuse that came out. And so, because the clearing time is going to impact my incident energy on that circuit. So you can see we have different classes of fuses, class L, H, K, RK. A lot of this is going to be determined by voltage and clearing time. And so a lot of these fuses can be used in different uh, types of systems. And but a lot of it is going to be voltage dependent on what class of fuse you would get. Also, some of these will be current limitation. So a class L fuse, definitely current limiting fuse, that is going to help us reduce the amount of incident energy that could be present at that facility. And so I already said this, that if we are going to check and replace a fuse, the safest way is this. We want to de-energize this whole disconnect. And so I am going to go to the upstream overcurrent device, wherever that is. I am going to perform uh, the steps needed to establish an electrically safe work condition. So I'm going to find the source for this. I am going to make sure that I have shut off the equipment. These fused disconnects are not load break devices. So first I'm going to hit a stop button or whatever it takes to have no current flowing through this. And then I am going to uh, shut off the upstream overcurrent device and perform live dead live here. I will have already locked and tagged out that upstream overcurrent device. Once I have determined that there is no voltage present here, I will get a insulated fuse puller, pull these out, and I will go ahead and find out if it says 0 ohms and the fuse is good, or I will find out if the meter says OL, open line, and the fuse is bad. Uh, One important thing here I do want to reiterate. When I install these fuses back in this fuse disconnect, I want to make sure they're turned so that I can read the information, because all three of those fuses, they better be identical. And so let's say that we have a three-phase motor. That three-phase motor has identical windings in it. And so I need identical fuses here. And remember, we can't just randomly change these fuses to a different size or a different class, because it will change our clearing time, and that could impact safety. So, now, I also did say this, that we can check these while they are energized. And so OSHA does allow us to do this. They're calling it troubleshooting, but we do have to wear the proper personal protective equipment. So hopefully you have arc flash warning labels in your facility, and you can make that determination based on the incident energy and voltage that is present at this disconnect. If I am going to uh, go ahead and replace those fuses, here is a picture of the insulated fuse puller. They also make a yellow one. But let's take a look at this fuse over here just for a second, and I'll zoom in on it. So LPS, RK, 300 SP, current limiting, dual element, time delay fuse, low peak. And so low peak sensing right off the bat. What does that mean? That means that our sine wave will not even get a chance to get to the peak before this fuse is going to open up and protect that circuit. That happens extremely fast, in even a half a cycle. So if we replace this fuse, we're going to lose all those characteristics of that fuse. And so we've got to replace it with the exact same type that is in there. And so, of course, if I am going to replace it, make sure I am de-energized. The only fuses I could replace energized would be something that would be below 50 volts. So maybe some control fuses for my control circuits, if there was no other voltage present in that cabinet above 50 volts. And do live, dead live, wear my PPE, and get that fuse replaced. Make sure it is the exact same one. The voltage rating is the same, the current rating is the same, and the interrupting rating is the same, and the same class. So important when we replace them. Now, if we are going to want to check these for whatever reason while they're energized, OSHA gives us only one method to do this, and they call this the crisscross method. And so there are times when I just can't de-energize and I have to troubleshoot a little bit. Right now, I'm not checking any fuse. I'm just verifying that I have my incoming power to the line side of my fuses. So between A and B, I have 480. Between A and C, I have 480. And B and C, I have 480. So I see that I have the proper voltage on the line side of my fuse. And so remember, I called this the crisscross method, which means I am going to take one lead and put it at the bottom of an opposite fuse. And so I put one lead on the line side of A, I take the other lead on the load side of C, and I don't see 480 anymore. Well, what does that mean? That means that this fuse is open. It's not allowing that 480 to make its way to the bottom of that fuse, and I now have found my defective fuse. If I continue with the crisscross method, notice I'm still on the line side of A. I could go on the load side of B or C. When I go to B, I see the meter does say 480. So phase B is a good fuse. And I come to C, I know that phase B is still a good fuse. I go to the load side of phase A, that is a good fuse. So the only fuse I found bad here was phase C. And so phase A is still good, continuing with the crisscross method. This is what OSHA does not want us to do. They do not want us to check a fuse while the equipment is energized when we go from the top of the fuse to the bottom of the fuse with our meter. Because notice, we were reading before 480 volts. All of a sudden, I went to 238. And so now my fuse is in series with the windings of that motor. And so if I do this, right, I could energize something on the load side of this, or I'm going to get some false readings. And so they do not want us to go from the top to the bottom while we are energized. That is just going to be a no-no. So I noticed that we do have some questions in the Q&A, and I am going to turn it back over to Ryan, and we are going to address your questions right now.
Thank you very much, Bob. This has been a pleasure learning more of the ins and outs of the different types of circuit breakers, what they do, and maybe busting some of the myths. I know I'm sure a lot of people out there do still believe today that circuit breakers there and designed to protect us from an electrical shock necessarily, but definitely not necessarily. So we got a few questions, and I'm definitely highly encouraging everyone listening in that if you have a question, now is your time to ask it in the Q&A box. Go ahead and click Q&A, type a question, it'll come to us and we'll be able to get to it before we close up shop today. The first question we have for you, Bob, is about the insulated case circuit breaker, ICCB, and the low voltage circuit breakers. Do those work also on 80% operational? I take that to mean maybe 80% load. But yeah, how would you comment on that?
No, those operate on 100% of the load. Only the molded case circuit breakers, the real small ones that we would have in our house or still in our facilities, those are the ones that operate on 80% of the load. The uh, the larger circuit breakers, they can operate at 100% of the load. That's a great question.
Uh, Bob, this is a term I'm not too familiar with, but maybe you can help with the term of a protister. And what is the difference between a dual element fuse that we talked about and something called a protister?
Wow, I'm not sure on that question.
Yeah,
I have
I,
never heard of that term either. So I don't know what that term is. And I can tell you this, if somebody asks me a question that I don't know, I am going to tell you, I do not know. So that's why I love teaching, right? Because I always learn something. So before I go to bed tonight, I will go ahead and find out what that is, but I have never heard that term.
Sounds good. Yeah, and for this individual asking this question, this is a perfect opportunity for us to spend more time together with you in a 2-day class and really talk in more detail about these. It looks like it might be even a brand name I'm noticing on Google anyway. AJ says, in most cases, aren't circuit breakers the standard versus fuses? And when would be the case we'd actually use a fuse over a circuit breaker?
That's a great question. And in today's world, he is right. They are pretty much the standard, uh, and mostly because of their convenience is why they're the standard. But we sometimes will use fuses because of this. Let's say that we want to be more responsive to overloads. Fuses are better with overloads than the bimetallic pieces of metal that have to bend. And so fuses do a very good job with overloads. That's why we might use them a lot of times in a motor circuit. They could help us a little bit with the actual overloads that we have put in the circuit, some. And of course, control fuses are really, we really want those for overloads because you usually utilizing a smaller voltage and a smaller amount of current. The circuit breaker, the bimetallic strip, would never have enough current going through it to protect against an overload on a control circuit. So most of the time, if you see fuses in there, they're going to be in a control circuit, a motor circuit, or something that we really need to protect against overloads on. That's a great question.
Excellent. Um, are fuses different, maybe in standards or size and shape, let's say, between European and North American type of fuses?
Uh, yes, and they are. You're right. So uh, with the IEC, or the International Electrotechnical Commission, sometimes they will construct those fuses just a little bit different. But with NEMA here in the U.S., that's basically what I went through, was all NEMA stuff, because I live in the U.S. and that's what I grew up with. So, but they are constructed just a little bit different, but they pretty much will go ahead and still still do the same job, just that they were constructed just a little bit different. So,
Excellent. Let's see here.
hey, guess what on
Yes.
that protester fuse?
Yes.
Okay, here's what they're using. They're using some electronics inside the fuse, some semiconductors to
Hmm.
interrupt the current instead of fusible links. So it's not going to melt, but it is going to be an electronic type of a fuse. So
Mm.
whoever asked me that question, that was a great question. And I had to ask my assistant that's in the room, who is an electrical engineer, and he came up with that answer fairly quickly for me. And
Wonderful.
I told him, thank you for that. They are fast acting, also, by the way, he added, but
Excellent.
they are an electronic device.
Good. That's excellent. A team approach, really, with our wide variety of instructors at the table and experts.
Stan Turkle knows everything.
Oh, yes, absolutely. Let's see. Um, how about the idea of cool off? So when we experience an overload, this user presumes that when those bimetallic strips get heated up, they bend and cause the tripping process to begin. Would there need to be a cool off time then for them to reset?
On yeah, yeah, there is a cool off time, and
Hmm.
so that's good. And the cool off time depends on the manufacturer. So with circuit breakers, if it was a long overload where the heat really got a chance to build up for an extended period of time, the cooling down period would be longer. If it was a short circuit or a ground fault situation, then the heat really never had a chance to build up much, and so we're using the magnetic element in that case, and you can reset those almost instantaneously after it happens. But if it if it is a situation where it's an overload, the cool off time is a little bit longer.
Mm. Bob, what would you recommend to this attendee who wants to know your recommendations for fuse and circuit breaker maintenance?
Okay, so that's great. I love that question. And so first I'll start with circuit breakers. And so I am going to give you an idea what the manufacturer says about circuit breakers. So if we're talking about molded case circuit breakers, and there we should definitely exercise them once a year. We should do thermography to make sure that there are no hot spots where the breaker is. We should check the torque setting of that breaker at least once a year. And if we have the time, it has plastic insulation on it. It would be real nice to make that breaker out. Now, larger breakers where they might be racked in and out, that's going to be a little bit different because there's going to be a much higher um, chance of arc flash there because of the incident energy. And I can tell you there, we'd want to rack that breaker out. We want to ohm out the contacts. Uh, we want to maybe use some electrical cleaner, brush it all up, vacuum any dust out of there. I would never use compressed air, but uh, rack it back in, check the mechanism, make sure we can energize it, adjust any of the trip settings, make sure that they are still in the range that we want them at. And we could also do current injection to make sure that the circuit breaker was going to trip at the desired clearing time under a short circuit or ground fault or overload. So current injection is used a lot on the larger breakers. On the smaller breakers, that visual indication with we want to make sure that we exercise it, do some thermal imaging, and maybe also do the torque setting and get the mega out if we want to. On
Absolutely.
fuses, pretty much we're just going to keep them clean because that's about it. Look for corrosion, look for hot spots. So I have seen the fuse holder lose its mechanical integrity. That's where a thermal imager would be extremely handy for us to pick up any hot spots. But keep them clean and do thermal imaging, and you should be in pretty good shape on fuses.
And to follow up on some of those tasks that you were mentioning for maintenance, thermal imaging, doing the vacuuming maybe a little bit, those kind of things. How often would you recommend we do some of those maintenance type of activities? Are we talking annually or maybe less often or more often?
Annually.
Annually?
Great question. Yeah.
Definitely. It's good to keep that annual routine down so we don't lose track of anything. And as we're doing these tasks, one more follow up on that would be what should we look for to let us know that that circuit breaker is in the borderline condition and might need to be replaced?
That's another great question. So immediately, I would take a look at when I exercise it. Did it snap right back on? Really, really nice. I would take a look to see if there's any cracks in it. I would look to see if the circuit breaker had any failures in the past where there might be some arcing involved, and that would be some really good indications. I would also take a look at my load and maybe put an amp clamp around the conductor on the load side to see if I am reaching that 80% mark of current flowing through it. And if I am, if my load is a continuous load and if it's on for 3 hours or more, and that breaker has been utilized at the upper range of its current carrying capacity, it might be time that maybe I'm going to then come in with some current injection and determine that the circuit breaker would still clear the condition in the desired clearing time range.
Excellent. Thank you so much, Bob. That a lot of people are curious, kind of on the maintenance side of these circuit breakers, with a lot of technicians here. One particular that's I see coming here is kind of the number of trips. What do you find some of the manufacturers tend to average on number of times these circuit breakers can be actuated and tripped before they should be replaced?
That's a great question. So, normal circuit breakers, uh, there really is no upper parameter on the number of trips that they can encounter as long as we have kept the current in under the interrupting rating. We should have some arc shoots in that breaker to make sure the contacts are still good. But what comes to mind on that question more so than anything is GFCI circuit breakers. So the manufacturers are now allowed, because of the UL 943 standard, to build in an end of life cycle on the GFCIs. That number is dependent on the manufacturer. But let's say that the GFCI circuit breaker experiences 15 ground faults and it is tripped 15 times. The manufacturer could have programmed in that 15 trips is the end of the life of that GFCI circuit breaker. And that means that that GFCI circuit breaker is not going to give us power anymore when we reset it. And we are going to have to go and replace that circuit breaker. But that's the only type that really has an end of life cycle. As the other ones, as long as we use them within their parameters, they should last a really long time. For example, I installed circuit breakers in 1971, and if we go back and look at those breakers today, as long as they were maintained properly, they are operating the same today as they did when they were installed in 1971. So,
Yeah, those serving a full life out there in the field. Excellent. And yeah, that we always find that people who are not maintaining properly end up getting even a year or less on some of these things, and they just keep replacing them, and they wonder why their budget is being busted with all their product replacements. So here's another interesting term, and I'll just remind everyone we got less than 10 minutes left before we're going to be wrapping up, so we're going to try to answer as many of the remaining questions as possible here. Another interesting terminology I'm seeing here, Bob, that I'm not too familiar with, maybe can help, is amp traps. How would amp traps differ from a fuse? And is there any effect to those testing procedures with an amp trap?
I am not sure on that one either.
Neither.
So
I haven't heard that one before.
that's I haven't heard that one either. So that's a
There's
good one.
definitely we don't want amps to get trapped anywhere. I know that much. They got to flow somewhere. They got to flow back.
That's true. That's 100% true.
Right.
And I don't know exactly why they call them amp traps, because they're it's just a it they're just a fuse. I mean, that's it.
Hmm.
They're just a fuse, and
Right.
that's
Definitely.
all they are. I don't know why they call them an amp trap.
No problem. It's interesting to see all the different perspectives here at the table.
Right. And that's another pet peeve of mine is terminology,
Yes.
because I teach so many different classes. I'll go into a National Electrical Code class. Some people will call uh, a 4-inch square junction box a 1900 box. Other people will call it something else. And some people call my overloads for motor heaters. It just there's a lot of different names for different things. And um, I got to believe that this amp trap could be just a specific class of a fuse, or maybe a manufacturer's name. Sometimes I'll call a split bolt connector a burndy, but terminology sometimes can kill us. But these are the amp trap is pretty much just a it's just a fuse. I mean, that's all I can tell you.
Right. Definitely. Would you say environment of where some of these circuit breaker panels are installed play a factor in their capacity? In this person's example, if it was placed outside on a wall where the sun shines directly on it half the day, could there be a possibility for those circuit breakers to have a reduced capacity, let's say, because of all the heat that's being
Sure.
generated?
So there's no doubt about it that it could add to that. Here's another concern that I have with the environment is if we're not installing these fuses or circuit breakers in the right enclosure, we've got to worry about temperature change and condensation and corrosion impacting uh, the condition of the breakers or the fuses. But environment is a huge consideration for us. And so we have to keep that in mind all the time and make sure we get them in the right enclosure. If we want to maybe help a little bit with that, we can put a fan in, or we're getting equipment now that will come with its own air conditioning right inside to keep the equipment cool. And so if reliability is our issue, we can keep that equipment cool by putting some AC right inside the equipment and
Mm.
keep everything uh, to a temperature level that it would operate perfectly all the time.
Definitely. I think the last question we can get to, unfortunately, sorry for those of you we weren't able to get to your question. Definitely do get back in touch with us by calling this number, 847-808-4000. Talk to me or Bob if you like. We can get set up with a talk to you and chat more with you about the opportunities to continue learning. So I think this last question I'll pose to you, Bob, is really what you had mentioned about the switching grade circuit breakers. And do you have any reservations like this individual does about even if they are switching grade, they don't really like using them as a switch. Do you express a similar discomfort there, would you say, or are you saying, you know what, if it's switching grade, it's perfectly fine to be used interchangeably with an actual switch?
Well, that's a great question, and I'm going to go on my experience. So we put in some SWD circuit breakers in schools back in the 70s, and the gym teacher would come in dressed in shorts and a t-shirt and be turning the gym lights on with SWD breakers. And so those were installed back in the 70s. Here it is, right? 2021. Those same breakers still turning on the same lights. No issues. And so it goes back to this: if they've been maintained properly, there should be no issue. The problem is we have so many molded case circuit breakers in this country. Sometimes it's hard to find the time to do the proper maintenance on all of them. But if they've been maintained properly, they have a UL listed for a switching device, then we should be able to use them in accordance with those UL instructions.
Definitely. Thank you so much for your wisdom today, Bob, and thank you everyone for being here today. We really appreciate you taking the time to learn a little bit more about fuses and circuit breakers, and just know that the learning doesn't end here. First of all, there's a lot of public webinars for you to peruse on the TPC training website. Under our recorded webinars page, we've done countless of these over the last just 12 months even. So check those out. Call us up if you want some more training on this, and we will be in touch. Thanks so much and have a great day.